Hi friends, this is Naresh. This is my 12th lecture on mechanics of solids or strength of materials subject. This subject is common for second year B.Tech and second year diploma mechanical students. Okay. In this session, I am going to explain about stresses induced in composite bars and composite tubes. In this session, I will explain with examples. First of all, you have to know the fundamentals about stresses induced in the composite bars. Here I consider this one as a composite section. Okay, this is a fixed plate and this is a one bar, this is another bar. These two are having different cross-sectional areas and same lengths. Here these two bars having same lengths. Okay, so a composite bar may be defined as a bar made up of two or more different materials joined together in such a manner that the system extends or contracts as one unit. Okay, one unit equally when subjected to tension or compression. In case of composite bars, the following points should be kept in view. Okay, so కాంపోజిట్ బార్ అని మనం ఎప్పుడు అంటామంటే ఒక టూ ఆర్ మోర్ బార్స్ ని ఒకదాని పక్కన ఒకటి కానీ ఒకదాని లోపల ఒకటి కానీ మనం ఇన్సర్ట్ చేసినప్పుడు కానీ ఒకదాని పక్కన ఒకటి ప్లేస్ చేసి కలిపి ఒక బార్గా మనం యూజ్ చేసినప్పుడు దాన్ని కాంపోజిట్ బార్ అంటామండి. సో ఆ కాంపోజిట్ బార్ అనేది ఈక్వల్గా ఎక్స్పాండ్ అవ్వటం కానీ అంటే అన్ని బార్స్ కూడా ఈక్వల్గా ఎక్స్పాండ్ అవుతాయి లేదంటే ఈక్వల్గా కాంట్రాక్ట్ అవుతాయి. సో ఎక్స్పాన్షన్ అనేది ఎప్పుడు జరిగింది అంటే టెన్సైల్ లోడ్స్ యాక్ట్ అయినప్పుడు ఎక్స్పాన్షన్ జరిగింది. ఓకే అండి. కంప్రెషన్ ఎప్పుడు జరిగింది అంటే కంప్రెసివ్ లోడ్స్ యాక్ట్ అయినప్పుడు కంప్రెషన్ జరిగింది. సో సో దిస్ ఈస్ ది ఎగ్జాంపుల్ ఫిగర్ ఫర్ కాంపోజిట్ బార్స్. ఓకే, ఇక్కడ మీరు ఇందులో ఒక 2 పాయింట్స్ గుర్తుపెట్టుకోండి కాంపోజిట్ బార్స్ లో. సో ద ఎక్స్టెన్షన్ ఆర్ కాంట్రాక్షన్ ఆఫ్ ది బార్ బీయింగ్ ఈక్వల్, the strain that is the deformation per unit length is also equal. Okay, the meaning of this point is the change in length or change in diameter in bar 1 is equal to change in length or change in diameter in the bar 2. Okay, so the total external load on the bar, is equal to sum of the loads carried by different materials. Okay, the meaning of this line is the total load acting on the compound bar or composite bar is equal to the load shared by the bar 1 plus load shared by the second bar. Okay, so the total load carried by the compound or composite bar is equal to the sum of the loads acting on the each bar. Okay, so here you have to remember that the total deformation or total strain or total elongation or total contraction in each bar is equal to each bar is same. Okay, so and also the total load carried by the compound bar is equal to the sum of the load carried by each bar. Okay, here each bar having a different load carrying capacities because it depends upon the load carrying capacity always depends upon the strength of the material. So that strength always depends upon the Young's modulus of the material. So if you are using same material, then each bar having a same strength, but in our composite bars we are using different materials. Okay, if you are using aluminum as one bar and steel as another bar. Then steel materials having high Young's modulus, that is nearly 200 to 210 200 gigapascal, but aluminum has only 70 gigapascal. Okay, that's why the strength of the steel material is more than the strength of the aluminum bar. So then the load carrying capacity of the steel also more than the steel carrying capacity of the aluminum. Okay, so here, so in composite bars, the very important point is Young's modulus. Young's modulus is the important property of the material. So in our problems, we have to consider individual Young's moduluses. Okay, Young's modulus means uh, the ratio of stress by strain. The ratio of stress to strain is called Young's modulus. Young's modulus also known as modulus of elasticity. Okay, so in our problems, you must know the values of Young's modulus for each bar. Okay, that is very important because the expansion or contraction of the materials and load carrying capacities always depends upon the elastic property. Okay, so and now I am explain the formulas used in our composite bars. Here, consider a composite bar made up of two different materials like this. This is the isometric view, this is the sectional view. Okay, I consider this one as a bar 1, this one as bar 2. Okay, and the length of each bar is same. So the total load acting on the compound bar is equal to P. Okay, so then P1 is the load acting on the bar 1. Okay, and P2 is the load acting on the bar 2. Okay, then P1 equal to load carried by the bar 1, and A1 is the corresponding cross-sectional area of the bar 1, and sigma 1 is the stress induced in the bar 1. Okay, so E1 is the Young's modulus of the bar 1. Okay, so these are the values for bar 1. Okay, similarly P2, A2, sigma 2, E2 are the corresponding values of bar 2. Okay, so here the load carrying capacity always depends upon Young's modulus. So here E1, E2 are the different materials. Okay, different material Young's modulus are different for different materials. So here I consider E1 as one material and E2 for this material. Then the load carrying capacity also different. So P1 is the load carried by the bar 1, P2 is the load carried by the bar 2, and A1 is the cross-sectional area of the bar 1, A2 is the cross-sectional area of the bar 2. Okay, and if the loads carried by each bar is different, then the stresses also different. Okay, so the stress sigma 1 is the stress induced in the bar 1, sigma 2 is the stress induced in the bar 2. Okay, so here I considered original length of each bar is the same. In this condition I consider the length of each bar is same. Then I consider L is the original length. Now when you are applying tensile or compressive loads, then the deformed shape I consider as delta L. Okay, I consider deformed length as delta L. So here the elongation or contraction or deformation of the composite bar equal to delta L. Okay, delta L is the total elongation or change in length. Okay, now from already we have discussed in previous slide, the total load P is the total load acting on the composite bar. Then the total load P equal to load carried by the bar 1 plus load carried by the bar 2. Okay, so the total load P equal to P1 plus P2. P1 is the load acting on the bar 1. P2 is the load acting on the bar 2. Okay. So here uh, the stresses sigma 1 is the stress induced in the bar 1. Then sigma equal to the already we know the formula stress equal to load by cross sectional area. So the load acting on the bar 1 equal to P1 by cross sectional area of the bar 1 equal to A1. So P1 by A1 is the stress induced in the bar 1. Okay. Similarly, the strain already we know the formula for strain equal to delta L by L, and also another formula is there, that is stress by Young's modulus. Okay, stress by Young's modulus is the another formula. So strain equal to stress by strain. So for bar 1, the strain induced in the bar 1 equal to stress induced in the bar 1 divided by Young's modulus of the bar 1. So here substitute value of sigma 1 equal to P1 by A1. Then the strain equal to P1 by A1 into E1 is the equation of strain. Okay, and already we know the formula for another formula for strain equal to change in length by original length. Okay, already we know the formula for change in length equal to here strain equal to sigma 1 by and a stress by strain, or delta here delta L by L is another formula. Okay, delta L is the deformed length or deformed length or change in length. So here already we know the strain. So strain equal to P1 A1 E1. Then if you want to find out the value of change in length, then strain into original length is the formula for change in length. So you have to substitute the value of strain equal to P1 by A1 E1. Okay, so P1 here L is there, so P1 L by A1 and E1 is the formula for change in length. Okay, this is the formula for change in length in bar 1. Okay, so by using this formula, okay, you have to find out the deformation produced in the bar 1. Okay, here this is the formula for change in length in bar 1. Similarly, the change in length for bar 2 equal to same formula, but the load acting on the bar 2 equal to P2. Just to substitute P2, and A2 is the cross sectional area of the bar 2, and E2 is the Young's modulus for bar 2. Okay, so here I consider L. L is the original length is same for bar 1 and bar 2. Okay, here already we discussed in previous slide, in compound bar or composite bars, the stress or the strain or deformation produced in each bar is same. So the deformation means a change in length or change in diameter. Okay, so from the definition of the composite bars, the strain or change in length in each bar equal to same. So that's why the strain in bar 1 equal to the strain in bar 2. This is the relation from composite bars definition. Okay, so here you have to substitute values of delta L1 and delta L2. Okay, so then L is the same, so you have to cancel the length L in both sides, and P1 P2 here P1 by A1 P2 by A2. Here the stress P1 by A1 is the stress, P2 by A2 is the stress. Here the stress also same in compound or composite bars. So then you have to cancel P1 by A1 equal to P2 by A2. So then just sigma 1, P1 by A1 is the stress sigma 1, and P2 by A2 is the stress in bar 2. Okay, so this is the formula for composite bars. Another formula also is there from by using this equation. Okay, already we know the uh, total load acting on the bar, compound bar equal to P equal to load acting on the bar 1 plus load acting on the bar 2 equal to, here already we know the formula for stress equal to load by area. Already we know the formula for stress equal to load by area. Okay, so here then load equal to stress into area, so load P equal to stress into area. So this is the formula for load. So for load 1, P1 is the load acting on the bar 1 is equal to stress induced in the bar 1 into cross section area of the bar 1. Okay, similarly P2 is the load acting on the bar 2, then sigma 2 into A2 is the value of P2. Okay, this is the one equation for finding out the total load acting on the bar. And these are the another formulas for determining the individual stresses. Okay, sigma 1, this is the relation between stresses and Young's moduluses. Okay, sigma 1, if you want to find out the stress induced in the bar 1 in terms of sigma 2 and Young's modulus, then E1 by E2 into sigma 2 is the formula for sigma 1, that is the stress induced in the bar 1. Similarly, sigma 2, from this relation, these two are obtained from this relation. Okay, you can observe here carefully. Sigma 1 equal to, you have to move this E1 into right side, then E1 by E2 equal to sigma 2 is the formula for sigma 1. Similarly, is sigma 2 equal to E2 by E1 into sigma 1. Okay, these two formulas are obtained from this equation. Okay, similarly, another formulas are there to determine the load carried by the each bar. That is P1 is the load carried by bar 1. Then if you know the value of total load acting on the bar and the individual areas and individual Young's modulus, then you can use this formula to determine the load carried by each bar. Okay, this is the formula for load carried by bar 1. Similarly, the load carried by bar 2 equal to P2 equal to P into A2 E2 by E1 E1 A1 plus A2 E2. Okay, so by using these two formulas, you can find the load carried by each bar. Okay, but another formulas are there. By using these formulas, so you can also find the value of P1 and P2. But in our problems, sigma 1 and sigma 2 are not given. Okay, so then by using these two formulas, you have to find out the values of loads. After getting the loads, individual loads, then you will get the values of individual stresses. Okay, so these are the important formulas used in our composite bars. Okay, so please by heart these formulas for solving the problems. Okay, these five formulas are very important in our problems. Okay, now I am going to discuss about problems on composite bars. This is the question. A bar 3 meters long. Here, a composite bar having 3 meters long. So the length is given. That is original length. Original length of the bar is made up of two bars. One of copper having Young's modulus 105 giga Newton per meter square, and other of steel having Young's modulus 210 giga Newton per meter square. And here each bar is 25 mm broad and 12.5 mm thick. This compound bar is stretched by a load of 50 kilonewtons. Find the increase in length of the compound bar and the stress produced in the steel and copper. The length of the copper as well as the steel bar is 3 meters each. Okay, friends. Here, one composite bar is there. That composite bar having a original length of 3 meters. Okay, so the initial length of the composite bar equal to 3 meters. It consists of two bars. Okay, so these two bars also having same length, each bar having same length. Here here I am using copper bar and steel bar for making the composite bar. Okay, here copper bar having Young's modulus 105 so 105 gigapascal. Okay, 1 Newton per meter square is called Pascal. So capital G is the giga. 105 gigapascal for copper. Copper, the Young's modulus for copper equal to 105 gigapascal. And also the Young's modulus for steel equal to 210 gigapascal. Okay, so here you can observe here the Young's modulus are different for different materials. Okay, here the steel material having high Young's modulus than copper. Okay, copper having low Young's modulus. Okay, that means the steel bar having higher load carrying capacity than the copper bar. Okay, here each bar is 25 mm broad and 12.5 mm thick. This meaning the cross section of the each bar is rectangular shape. Okay, the cross section of bar, each bar is a rectangular cross section. So here the width of the rectangle equal 25 mm and thickness of the rectangle equal 12.5 mm. Okay, now this is the shape of the composite bar. This is a fixed plate. Okay, here these two are the compound bars. Okay, so each bar having same length and same dimensions. Here this is the width equal to here the width of the each bar equal 25 mm. This is 25 mm, this one also 25 mm. Okay, one is copper, one is steel. Okay, so both are having same sizes. This is also 25 mm, and the thickness, that means this height equal to 12.5. This one also same. Okay, 12.5. Okay, so steel bar and copper bar both are having same dimensions and same length. Okay, but the Young's moduluses are different, so the load carrying capacity is also different. Okay, the load carried by copper bar is not equal to the load carrying by the steel bar. Okay, so this is the front view. Okay, this is the isometric view, this is the front view. Okay, so the cross sectional view is like this is a copper bar. This left side bar, I consider this left side bar as copper bar, and this right side bar I consider as a steel bar. Okay, this is the total load acting on the compound bar. Okay, 50 kilonewtons load acting on the composite bar. Okay, then you have to find out the individual loads acting on the copper and steel. Okay, that means you have to find out the load carried by the copper bar and the load carried by the steel bar. Okay, by using these Young's modulus values. Okay, yeah, this you have to consider this 50 kilonewtons as total load, that is capital P. Capital P equal to 50 kilonewtons, and P1 is the load acting on the copper bar, P2 is the load acting on the steel bar. So capital P equal to 50, 50 equal to P1 plus P2. Okay, the given data here, the length of copper bar equal to length of the steel bar. Here the length of copper as well as steel bar is 3 meters. So the original lengths are length of LC, C suffix C for copper and suffix S for steel. Okay, so length of copper equal to length of steel equal to 3 meters. Okay, 1 meter equal to 1000 mm, so 3000 mm is the original length. Okay, and Young's modulus for copper is equal to 105 gigapascal. 1 giga equal to 10 power 9, 10 power 9 newton per meter square, and also 1 gigapascal equal to 10 power 3 newton per mm square. Okay, so here kilo means 10 power 3. Okay, 1000 newton per mm square. Similarly, ES equal to Young's modulus for steel, that is 210 gigapascal, that is 210 giga Newton per meter square equal to 210 kilo Newton per mm square. Here the dimensions, the cross sections of copper and steel bar are same. So each bar having width equal to 25 mm and thickness equal to 12.5 mm. So the P is the total load acting on the bar, composite bar. Okay, so these are the given values in our problem. By using these details, you have to find the change in length, that is the increase in length. You have to find out the value of increase in length in compound bar, that is you have to find out the value of delta L. Okay, and also you have to find out the stress produced in steel and copper. Okay, so here I let delta L. Delta L is the change in length or increase in length of the compound bar. Okay, already the dimensions of the copper and steel bar are given. So by using width and thickness, you have to find out the cross-sectional area. The cross-sectional area is a rectangular shape. So the area for rectangle equal to width into thickness. So here width B equal 25 mm and thickness equal 12.5. Here the area of copper and steel both are same because these two are having same width and same thickness. So area C and area of copper bar equal to area of steel bar equal to 312.5 mm square. Okay, so this is the cross sectional areas. Okay, so these areas are used for finding out the individual loads. Okay, okay, this is the load carried by the copper bar. PC is the load carried by the copper bar. So already we discussed in previous. Okay, from these formulas, P1 is the load carried by the bar 1 equal to total load into area of the bar 1 and Young's modulus of the bar 1 divided by area of the bar 1 and Young's modulus of bar 1 plus area 2, that is the area of the bar 2 plus Young's modulus of the bar 2. Okay, this is the formula for load carried by the bar 1. Okay, so from this formula, PC equal to PC is the load carried by the bar, copper bar, and capital P is the total load acting on the compound bar, that is 50 kilonewtons. Okay, P is the 50 kilonewtons. So area of the copper into Young's modulus of the copper divided by area of the copper, Young's modulus of copper plus area of the steel into Young's modulus of the steel. Okay, so I am using this formula. Okay, so substitute all the values, P equal to 50 kilonewtons and AC, EC and ES all are given in our problem. So substitute all these values. You will get load carried by the copper bar. That is the answer is PC equal to 16.67 kilonewton. So this is the load acting on the copper bar. Okay, this copper bar carrying a load of 16.67 kilonewtons. Okay, out of 50 kilonewtons load. Okay, actually the total load acting on the compound bar equal to 50. Okay, in this 50 kilonewtons, only 16.67 kilonewtons load only acting on the copper bar, because this copper bar having low Young's modulus. Okay, so here steel bar having high Young's modulus. That's why remaining higher amount of load is acting on the steel bar. Okay, now already we know the relation, that is the total load. The total load P equal to load acting on the copper bar, that is a PC, and plus load acting on the steel bar, that is a PS. From this relation, you have to find out the other load, that is PS. PS is the load acting on the steel bar, is equal to PS. PS equal to total load minus load acting on the copper. Okay, by using this formula you have to find out the PS value. So that value is 33.33. This is the load acting on the steel. Okay, so the load acting on the steel bar equal to 33 kilonewtons, 33.3 kilonewtons load, and here the load acting on the copper bar equal to 16.67 newtons. Okay, so these are the loads acting on the individual bars. So this is the step 1. Okay, this is the answer for change in length or deformation or extension in the compound bar. Okay, so this one also is obtained from here. This is the formula for change in length. This is also change in length. Here delta L1 equal to delta L2. Already we discussed in this concept. For composite bars, change in length in bar 1 equal to change in length in bar 2. So by using delta 1 formula or delta 2 formula, you will get the change in length or deformation length. Okay, so I am using here, this is the delta L for copper bar, this is the delta L for steel bar. Both are equal, so you can take any one of these two. Okay, so this is the value of delta L, that is a change in length or elongation in the compound bar equal 1.52 mm. Okay, when you are applying a load of 50 kilonewtons load on the composite bars, then it will increase a length of 1.52 mm in downward direction. Okay, this is one answer, and then after you have to find out the stresses induced in copper bar and steel bar. So stresses produced in the steel and copper bar, you have to find here. So sigma s is the stress induced in the steel bar. Okay, so already we discussed in previous here. This is the here sigma 1 is the stress induced in the bar 1, sigma 2 is the stress induced in the bar 2. So by using these two formulas you have to find out the stresses. Okay, so the stresses induced in the steel bar equal to Young's modulus of steel by Young's modulus of copper into stress induced in copper bar. Okay, so sigma s equal to Es equal to 210 and Es equal to 105. Sigma c, the value of sigma c, we don't know the value of sigma c, so just you kept it. So the relation is sigma s equal to 2 into sigma c. This is one relation, and another relation is that the total load P equal to PS plus PC equal to sigma s as plus sigma c AC. By using this equation, okay, you have to find out the value of sigma c or sigma s. Okay, substitute the value of PS and PC values here. The value you can observe here, PS PS equal to sigma s and AS. So here sigma s equal to 2 into sigma c. So 2 into sigma c for sigma s, and AS equal to 312.5 plus sigma c into 312.5. Here AC and AS both are same, that is area of steel equal to area of copper. So here you sigma c is the only one unknown in this equation. So you can get the value of sigma c by using this equation. So the value of sigma c equal to 53 0.053 kilonewton per mm square. So the answer is 53 newton per mm square or 53 megapascal. This is the stress induced in the copper material. By using the relation sigma s equal to 2 into sigma c, okay, substitute the value of sigma c in this equation, you will get the value of sigma s. So sigma s is the stress induced in the steel bar equal to 2 into sigma c equal to 2 into 53 equal to 106 megapascal. Okay, so this is the answer for composite bar. Okay, now coming to the another problem. Yeah, this is a different problem. So this is a composite tubes problem. A central steel rod 18 mm diameter passes through a copper tube 24 mm inside and 40 mm outside diameter as shown in figure. It is provided with the nuts and washers at each end. The nuts are tightened until a stress of 10 megapascal is set up in the steel. Okay, so this is the diagram. Here a central steel rod, that is this one, this horizontal steel rod is having 18 mm diameter. Okay, and this steel rod is passes through a copper tube. Copper tube, this is a copper tube means a hollow pipe. Okay, the dimensions of copper tube, that is a 24 mm inside. Okay, the inside diameter is 24 mm and outside diameter is 40 mm. These are the dimensions for copper tube. This outside hollow pipe is copper tube. Inner diameter is 24 mm and outer diameter is 40 mm. Okay, this steel rod is a solid rod, solid shaft, that is 18 mm diameter. Okay, so this is a steel rod, this is a copper tube. Okay, this copper tube is a hollow pipe, so that's why this inside circle is 24 mm and outside circle is 40 mm diameter. Okay, this solid shaft is 18 mm outside diameter. Okay, these are the diameters. I will show the assemble view. This is the assemble view of copper and steel rod. Okay, by using these details you have to find out the stress induced in the copper and steel tubes. You have to find that values. So the given details are ds is the diameter of the steel rod. S suffix x, suffix s means steel, and suffix c refers copper. So ds is the diameter of the steel rod, that is equal to 18 mm. This is a solid rod. And dc1 is the inner diameter of the copper tube, that is 24 mm. And dc2 is the outer diameter of the copper tube, that is equal to 40 mm. Okay, already we know the value of stress induced in the steel tube. Okay, this value is already given in our problem. Sigma s equal to 10 megapascal. That is a stress induced in the steel tube equal to 10 megapascal. So by using these details, you have to find out the stress induced in the copper tube. You have to find out the value of stress induced in the copper tube. Okay, by using these diameters, first you have to find out the cross-sectional areas. As is the cross-sectional area of the steel rod. This steel rod is a solid rod, so a solid circular shaft. So the formula is pi by 4 d square is the formula for solid shaft. So d is the value of 18 mm. So as area of the steel rod equal to 254.5 mm. Okay, similarly, the cross-sectional area of the copper tube equal to, this copper tube is a hollow pipe. So that's why this is the formula for hollow pipe. That is a, you have to subtract the area of the inner diameter in a inner hole from the outside hole, outside circle. Okay, so AC equal to pi by 4 outer diameter square minus inner diameter square of the copper tube. So this is the area of the copper tube, 804.4 mm square. These are the individual areas. Okay. Here, sigma C is the stress induced in the copper tube. Okay, you have to find out the value of sigma C. Already sigma S is given, that is stress induced in the steel rod is given. But by using all these values, you have to find out the stress induced in the copper. Okay, so here this is the formula for strain. Sorry, formula for load acting on the steel rod. Here this is a copper, so this is a composite tube. In composite tubes, the load acting on each tube is same, but in composite bars problem, the total load equal to load acting on each bar, sum of the loads acting on each bar. But this is a composite tube. In composite tubes problem, the load acting on the each bar is equal to same. Okay, so here the load acting on the steel rod equal to load acting on the copper rod. Okay, so here already we know the value of sigma s, that is a 10, and area of the steel rod also we know that, and AC is the area of the copper rod. So by substitute all these values, you will get the value of sigma c. So here sigma c is the stress induced in the copper tube. Okay, this is the final answer for this problem. It is very simple. In our composite tube problems, you have to consider load acting on the copper rod equal to load acting on the in the steel. Okay. Okay, friends, thank you. uh, tomorrow class I will explain more problems on these composite sections.